In terms of bending moment, when it's my, we use what? Iyy. Okay, I want you all to look at the trend. Okay, now based on this, the first term over here is due to torsion. This term over here, the shearing stress is due to Vy. Over here, the shearing stress is due to Vz. Over here, this is due to our axial load. And over here, this is due to the moment about the y-axis. Over here, this is due to the moment about the what? About the z-axis. Okay. Now, why I do this is I want you to look at the pattern of the formula, right? In the shearing stress, when you have Vy, you divide by what? Izz. When you have Vz, you divide by Iyy. Whereas in the normal stress, when the bending moment is about the y-axis, you divide by the I about yy. When the moment is about the z-axis, you take about Izz. Okay, so there is a very distinct difference. Now, if we were now to focus in our shear now, okay, let's focus on our shear. Now we are going to have a tube. Okay, we're going to have a tube. And our tube is built in. Okay, and then this is our axis of interest. And then this is our tube. This is our axis. And then if I were to sketch our transformation, okay, that's SYZ. So now, okay, if our structure is under a torque about the x-axis, right? And then we have a force coming down in Py. Okay, we have a force going in Py. Okay, that's all we have. So we still know, right? This is at point A, and this is our point B. We know that point A or at this region is where failure will occur. Okay. So now, if we now look at the cross-sectional view, right? If we now look at the cross-sectional view now, so our cross-sectional view, this is our y, z, and our rotation about x. Okay. So now this is the cross-sectional view. Okay. Okay. This is our cross-sectional view. So now, what I want to highlight over here. Okay. So now, if we know, okay, the shear stress is equal to Tx over J, okay, multiplied by R. Okay. Now, how does this look like? Okay. So in terms of shear, now this distance over here, this is our radius, right? The vertical, right? This is our shear, right? So our shear stress now, right, is Tx r over j, we know the term over here, Tx, okay, we know the term over here, Tx over j, this term over here are constant, right? It will not change at all. And j, or let me define. So Tx is the torque about the x-axis, right? J is the polar second moment of area, and r is the radial distance. Okay, so we know this equation over here will have a linear distribution of your torque up to the radius. So at this point over here, the shear stress is equal to TR or Tx R max divided by J. Okay. So this is how the shear stress will distribute. And then we know by looking at the torque, if this is torque in the x direction, okay, this is torque in the x direction, the shear stress will look like this. Okay. Now, if we were going to place 4 elements, okay, no, I'll change the color. Cannot always. So we have element I, we have element J, element K, element L. Okay. So if we have all those elements, so I'm going to call element. Okay. I, J, K, and L. Okay. And the shear, all of them will be TR over J. I will call them as positive TR over J. Okay. I call them positive because I will declare going in the clockwise, we are going to call it positive. Okay. Now, on the other side, we have our shear. Okay, we will have our shear is equal to Vy over Izz Qz over T. Okay. So now I'm still going to place the same element over here. Element I, element J, element K, and element L. Okay. And we know the shear flow is coming from the top. Okay, Vy. So this point over here, this is known as our terminal. And this point over here is the other terminal. Okay. So now I'm going to sketch the shear flow. I'm going to sketch the shear flow. Again, the shorter length is give you lesser shear flow. The longer the length, the shear flow gets bigger and bigger. Okay, the shorter the length, it gets smaller. Okay. So what we see from here, right? What we see from there is when we have our shear stress, right, which is equal to Vy over Izz Qz over T, right? At point J and at point L, the shear stress is equal to what? 0. Because it's where the location of the terminal are. So the shear stress is 0 at point J. The shear stress is 0 at point L because it is point for element J and K are at the terminal. Okay. Okay. So the next thing that we want to see is we want to see at element I. If you look at element I, okay, I want you to pay attention on element I now. Okay, this is element I. And I highlight the arrow. If you look at the arrow of element I now, right? At element I, the shear stress is going in the upwards direction, right? Is doing this, right? The shear stress due to torque. Whereas the shear flow is coming what? Downwards. When this is the case, we will have minus Vy Qz over Izz divided by T. Minus. Okay. Now, which direction is positive, negative does not matter. For this case, right? For this case, I basically declare, okay, for this case, I basically declare clockwise as positive, right? And then for this case, I declare downwards as what? Negative, because it is opposing our shear flow or our shear stress due to the torque. Now, if you now look at element K, okay, if we now were to focus on element K, right? You realize that the shear stress due to the torque on the left-hand side and the shear flow due to the shear force at K is in the same direction. When that's the case, over here, you will have plus Vy Qz over Izzo divided by T. Okay. So how you add or subtract the stresses, it depends on is the direction is the same or is it different. Okay. So from here, you can see now that element K, right, will generate the power mass because you have positive over here, you also have positive over here. Whereas on element I, you have positive over here, down here is what? Negative. J and K will not fail at all. Why? Or I mean failure will not start from there because of the shear stress due to shear flow is equal to what? You can see over here, they are both equal to what? 0. Okay, very, very important that all of you need to visualize this. Okay, this is important. Okay, now as you can see from this formula, right? We have. I want you all to focus on the shear stress due to the shear force, which is By and Vz. Okay, so most of the time our shear force don't occur in a single plane. Okay, our shear force can occur in two directions. Okay, can occur in two directions. So now, if I'm now going to sketch a 3D diagram, so this is our X, Y, and Z, and this is our block. Oh, it makes my transformation looks off. Sorry. Okay. So now if we were to have our shear flow or shear